The other day, I recorded a video where I explained you what I think are faults in the design of Mavrik from Steadidrones. I'm still working on the machine to try to put it in flight, and this time what I want to do is to be a little bit more scientific and show you with measurements and some mathematical calculations those things the other day I pointed out. So as you can see, I got now some instruments, and we are going to start by analyzing the propulsion system. Motors, propellers, we are going to see the current consumption, the RPM at which the propellers are working, and then I will go further into other details. So let's go now to analyze motor, propeller, and current, RPM, and so on. As you can see here, I've got a digital oscilloscope, and this device is a Hall effect probe to measure DC current. First of all, we are going to measure no load current of the ACE motors of the drone. Well, we arm the system. Now we increase speed to maximum, and here you can see the waveform. Its consumption is now around 7 amperes. Okay, 7 amperes. I'm going to stop this. Seven ampere is quite normal because we don't know the specifications of the motors. It means they are around a no load current of 1 ampere per motor. Well, I teach electrical machines, and I found this quite normal, and the motors seem to be, well, reasonably good. Let's go now to the propeller. I'm going to move this to the side. The European company that distributes this product is a Czech company, sent this drone with this propeller. This propeller is an APC propeller. I'm very familiar with this kind of propeller because I've been using it from the very beginning for small planes, for pack flyers. As you can see, it's completely flexible. It's not a rigid propeller. We think what should be used is this type of propeller, a T-motor propeller of carbon with a very good mechanical resistance. First, I'm going to measure RPM with this digital tachometer to find out if the manufacturer has taken into account this propeller shouldn't run above 4,500 RPM. I'm going to be careful because this is a quite dangerous operation, so I will be on the other side. Well, as you can see, I've only started and it tries to go up. thrust is huge, incredibly huge. In fact, it is difficult for me to hold the drone. I will try to do it from here to see if I'm able to keep it stable and measure the RPM. I will check it's not going to cut my hand. Okay, guys, you can make this test and you will see how funny is the design. Propeller has been running 5,600 RPM, 1,000 RPM more than the maximum speed indicated by APC in its website. So this propeller is running in a stall. I'm not talking about the possibility of having flutter and all kind of troubles. So we are almost at 25% above the maximum RPM this propeller should have. So you can imagine how the control system is going to work. I've also checked the consumption and it is 25 amperes. So it means the system is now, if we've got 8 motors with these propellers at maximum throttle, they will be absorbing from the battery 200 amperes. Let's go then to the next thing, the battery system. I'm going to unplug this battery and I'm going to show it to you. Shut up. This is one of the batteries. It is 10,000 milliamperes that was provided by the manufacturer. And the other battery, which crashed in one of the attempts of trying to fly this, is 8,000 milliamperes. Okay, if we are going to work with 200 amperes at maximum throttle, it means we need to work with 20C in this case. This battery should be 20C, and in this case, this should be, well, a little bit more, around 25C. We have no idea about the kind of battery. I can only tell that this drone never flew, in fact, and both batteries are really damaged. It is quite difficult for me to believe these batteries are capable of giving 25C with this high capacity, but okay, we must believe this is true, and this should be 30C to work with a minimum margin with respect to the consumption of the propeller. So here we've got the same, the first fault, and this is something that is not an opinion. It is simply measuring the rotating speed of the propeller that is 1,000 to 300 more than the maximum speed for this kind of material. Honestly, I don't very much like repeating this test because I see I'm going to end without a finger. But we are going to do it now with the T-style propeller. I expect a similar RPM and a similar consumption, but of course less vibration and no fluttering on the tips of the propeller or anything like that. Let's try to do it then once more. Okay, RPM are almost the same. It's 5,500, and the consumption has increased a little bit. It was 25 point something before, and now it's almost 28. But as you've seen, I think there's less vibration and the sound is much more normal than before. I'm going just to run it to you to see, to let you notice. I'm going to put it closer and turn the light off. To let you see the difference between this propeller and the previous one of plastic. Although I've balanced the propellers, and I think they were quite well balanced, I'm going to rebalance everything because it still vibrates a little bit. If I hold here the tube, I feel a certain amount of vibration. But at least this design is not going to be flexible.